Have you ever looked up at a full moon and watched it slowly get swallowed by the darkness? It's one of the most incredible sights you can see from your own backyard, a grand cosmic spectacle playing out right above our heads. It's a lunar eclipse. But here's the thing, something really weird happens once the moon is deep inside that shadow. And that's the beautiful mystery we're diving into today. Logically, when the Earth completely blocks the sun, you'd think the moon would just vanish, right? Go completely black. But instead, it often does the exact opposite. It transforms, glowing with this deep, coppery, sometimes blood-red light. So the big question is, how on earth does a shadow, the total absence of light, end up creating something so vibrant and so full of color? To figure that out, we're going to take a journey right into the heart of that shadow. We'll start with the basics of this cosmic alignment, then we'll find out why eclipses are actually pretty rare. We'll dissect the shadow itself, crack the mystery of the blood moon, I'll give you a guide for how to watch one, and finally, we'll see how this whole spectacle is actually a powerful tool for science. Okay, let's start at square one. What is actually going on up there? I mean, what does it take for the moon to just fade away from the sky? Well, it all boils down to a perfect cosmic game of hide and seek. So a lunar eclipse is, at its core, really simple. It can only happen during a full moon, and it's when our planet Earth slides directly between the sun and the moon. When that happens, our world blocks all that direct sunlight, casting this enormous shadow out into space that the moon just happens to drift right into. And here's that lineup, plain and simple. You've got the sun, which is obviously the giant light source. You've got the Earth, which is the object casting the shadow. And then you have the moon, which acts like a giant movie screen. For an eclipse to happen, all three of these have to be in a nearly perfect straight line. Now, people get lunar and solar eclipses mixed up all the time, so let's set the record straight. With a lunar eclipse, the one we're talking about, Earth's big shadow falls on the moon. They happen at a full moon, and the best part is, anyone on the entire night side of Earth can see it. That's literally half the planet. A solar eclipse, on the other hand, is the total opposite. The moon's tiny shadow falls on the Earth. They happen at a new moon, and you have to be in a very specific, narrow path to see it, which is why they feel so much rarer for any one person. So this brings up a really good question. If the moon goes around the Earth every month, and we get a full moon every month, why don't we get a lunar eclipse every single month? The whole setup seems so simple. Well, the reason is a tiny but absolutely crucial tilt. Seriously, think about it. It feels like it should be a monthly thing, right? Full moon, the sun, Earth, and moon are all lined up. Bam! Eclipse. But no. So what's preventing it? The entire reason comes down to this one little number, 5 degrees. That's it. This tiny tilt is why eclipses are special, rare events instead of just, a normal Tuesday night. But what's tilted? Okay, so check this out. Imagine Earth's path around the sun is a perfectly flat plane, like a giant cosmic frisbee. The moon's orbit around the Earth isn't on that same flat plane. It's tilted by those 5 degrees. So most of the time, when the moon is full, it's passing either a little bit above Earth's shadow or a little bit below it. It just misses. An eclipse can only happen on those rare occasions when the moon is crossing that flat plane at the exact same time that it's a full moon. The timing and the geometry have to be perfect. All right, so we've got the timing down. The moon has to pass through Earth's shadow. But it turns out the shadow isn't just one big blob of darkness. It has different parts. And to really get what's going on, we need to do a little shadow anatomy. First up, you have the umbra. This is the main event. It's the deep, dark, central core of the shadow. If you were floating in space inside the umbra, you wouldn't be able to see the sun at all. The Earth would be completely in your way. This is where all the eclipse drama happens. But surrounding that dark core is a much bigger, fuzzier, fainter shadow. That's the penumbra. From inside the penumbra, you'd look back and see the Earth only blocking part of the sun. It's like a twilight zone, not full sunlight, but not total darkness either. And you can see that two-part structure right here. Because the sun is a big disk of light, not just a tiny point, it creates this complex shadow. You have the dark, cone-shaped umbra tapering off into space, and then this much wider, grayish penumbra surrounding it. Which part of the shadow the moon travels through determines everything. And that gives us our 3 different flavors of lunar eclipse. The one everyone wants to see is a total lunar eclipse. That's when the entire moon gets completely engulfed by that dark umbra. Now, if the alignment is a little off and only a piece of the moon clips the umbra, we call that a partial lunar eclipse. You'll see a dark bite taken out of the moon. And finally, if the moon just skims through that faint outer penumbra, well, that's a penumbral eclipse. Honestly, they're so subtle, you probably wouldn't even notice the moon getting slightly dimmer unless you knew to look for it. And now we've arrived at the main event. We're back to that central question. Why, during a total lunar eclipse, when the moon is supposed to be in the darkest part of the shadow, why does it turn red? The answer, incredibly, isn't in space at all. It's right here at home, in our own atmosphere. So here's the secret. Earth's shadow isn't perfectly dark. Our planet is wrapped in this thin blanket of air, our atmosphere, and it acts like a giant cosmic lens. As sunlight grazes the edges of our planet, the atmosphere actually grabs that light and bends it, the scientific term is refracts it, channeling a tiny bit of it right into the shadow. And this is where the real magic happens. You see, sunlight looks white, but it's actually made of all the colors of the rainbow. As that light hits our atmosphere, the shorter, bluer wavelengths get bounced around and scattered all over the place by air molecules. This is called Rayleigh scattering, and it's the exact same reason our sky is blue. But the longer, redder wavelengths, they just power right on through, get bent by the atmosphere, and keep going into the shadow. So the moon ends up being lit by this filtered, secondhand, reddish sunlight. I think this quote from NASA just nails it. It is the perfect way to picture what's happening. The only light that reaches the eclipsed moon is the light that has just skimmed through the very edge of Earth's atmosphere, all around the globe. So from the moon's point of view, it's seeing every single sunrise and every single sunset on Earth all happening at the exact same time. All of that red and orange light gets focused and projected right onto the surface of the moon. It's beautiful. And look at this comparison. It tells the whole story. On the left is what an eclipse would look like if Earth didn't have an atmosphere. The moon would be almost totally black, basically invisible. But on the right, you add in our atmosphere and there it is, that familiar, beautiful, coppery red glow. Our air is literally the paintbrush for this celestial masterpiece. So now we get it. We know the physics. Let's make this practical. Let's say you're outside, you're watching a total lunar eclipse happen. What exactly should you be looking for? And why is it that no two eclipses ever look exactly the same? Well, believe it or not, astronomers actually have a rating system for this. It's called the Den-Jones scale, and it goes from L0 to L4. An L0 eclipse is super dark, the moon might almost disappear completely. And L4, on the other hand, is really bright and coppery orange. Most eclipses fall somewhere in between, around an L2 or L3. So what makes the difference? Well, it's all about how clean or dirty our atmosphere is at that moment. The eclipsed moon is basically a giant screen showing us the state of our own air. If a huge volcano just erupted somewhere, filling the stratosphere with dust, that'll block more light and give us a really dark L0 or L1 eclipse. But things like heavy cloud cover, big wildfires, even just general air pollution along the edge of the Earth can change the color. And of course, the moon's path matters too. A trip through the deep center of the shadow is going to be darker than just grazing the edge. And hey, for anyone who wants to see this for themselves, you're in luck. Go ahead and mark your calendars for March 3rd, 2026. There's going to be a total lunar eclipse visible for a huge part of the world. And then just a few months later, on August 28th, there's a nice partial eclipse. So you've got a couple of great chances coming up to see all this science in action. So to finish up, let's look at one final really cool idea. This amazing celestial event isn't just for show. For scientists, Earth's shadow is like a laboratory. It's a tool that lets us study our own planet from almost 250,000 miles away. The key takeaway here is that the Earth's shadow, the umbra, isn't empty. It is filled with sunlight that has been fundamentally changed by passing through our air. It's been bent, it's been filtered, and it carries the chemical fingerprints of our atmosphere with it out into space. So, by carefully analyzing that reddish light during an eclipse, scientists can learn a ton about Earth's upper atmosphere. They can detect things like volcanic dust or even measure the health of our ozone layer. It gives them real-world data to check their computer models. And get this, by looking through old historical records describing how bright or dark past eclipses were, they can actually find evidence of massive volcanic eruptions that happened centuries ago, giving us clues about our planet's past climate. But let me leave you with one final mind-bending change of perspective. Imagine, just for a second, that you're standing on the moon during one of these total lunar eclipses. You look up. You don't see a red moon. You see the sun completely blotted out by a giant black Earth. And wrapped all the way around our dark planet, you'd see this brilliant, fiery red ring of light. the combined glow of every single sunrise and sunset on Earth, all at once. So, in the end, it turns out our planet's shadow isn't about darkness at all. It's a lens. It's filled with color and light, and it tells the story of our home. And it just makes you wonder, what other incredible secrets, what other beautiful phenomena are out there in the universe, just waiting for us to find them? Not by looking into the light, but by looking carefully into the shadows?